Number 2. Toroid. What does a toroid look like? It's literally a solenoid that has been curled, right? So I'm going to draw the cross section of a toroid, or at least I'm going to attempt. So here's my best attempt. And then this has wires that go like this. Then I'm going to do a middle axis. I'm going to call this distance A and this distance B. Then I'm going to take a small dr. And I'm going to call this distance to the middle of it as R. The height of this, I'm going to call it H. And suppose the current is running through the wires that are coiled. What's a B field for a toroid? Where N is the total number of turns. Step 2, we are supposed to find the number of flux linkages, which is defined as N phi. But in order to find phi, we need to do integration, because unlike the solenoid case, this actually changes. So what is the dA in this area? This will be B H dr. Why? Because this is the area of the strip with width dr. So I can rewrite this as integration mu naught Ni divided by 2 pi r H dr. From A to B. Now I can take out everything that's constant. So I'll be left with that. Or phi B will just be mu naught N. Oh, shouldn't this be capital N? I messed that up. Shouldn't this be capital N? NIH divided by 2 pi log of B over A. right? That's the integration of 1 over r from a to b. So that means in order to make it the number of flux linkages, may I multiply both sides with n to give me n squared mu naught IH over 2 pi log of A over B. No, sorry, B over A. Then step 3 was, use the Flower equation to find inductance. So I'm just going to use my Flower equation to find my inductance, which will be L equals N phi B divided by I, or N squared mu naught IH log of B over A divided by 2 pi I. I and I go away, and I am left with L equals mu naught N squared H over 2 pi log of B over A. What do you observe about this? N, H, B, A, they're all constant, and they're all geometrical. They only depend on geometry. So again, L only depends on the geometrical factors. Woohoo!